we will have Hansol Suh, a student who's working at Argonne on implementing proximal projection-based solvers in Tau, and he's going to tell us about TaoADMM.
Cool. Okay. Hi everyone, my name is Hansol, and I'll be talking about the mini tutorial on ADMM, and at large it's more of a raising awareness of other new features coming up on Tau. So what is ADMM? It's called alternating direction of method multipliers. So you want to minimize a composite optimization, F plus G, subject to some kind of constraint. In this case, general case would be AX plus BZ equals to C. Here, capital is a matrix, and then lowercase is a vector. So here, F and G are convex, but not necessarily smooth. So let's say if G is a L1 norm, then it is convex, but not necessarily smooth. And we'll call L is the Lagrangian of this problem. So F plus G plus Y is a dual vector here, dual transpose residual of a constraint plus rho over 2. Rho, we'll call it a spectral penalty here, and then 2 norms squared of the residual. Now, ADMM, in a nutshell, you iterate over those Lagrangians. First, you minimize over X, and second, you minimize over Z, and then you update your dual vector, and that is the ADMM. So what would be a good example? Let's look at this tomographic example. On the right side is a simple 50 by 50 Shep-Logan tomography phantom. It's supposed to simulate how a human brain looks like or something like that. And one easy case to simulate it would be to minimize, you have this least square problem for F, which is essentially you're trying to solve some sort of a radon transform. And obviously, you want to regularize it, and let's just say you want to solve it with the L1 norm. Now, and how you turn that into a ADMM format is just turn the X in the your L1 norm into a Z, and then just subject to X minus Z equals to 0. Obviously, like I said, the L1 is not smooth, so it could be challenging for optimization. So this example, how would you run it? It's in the Tau constraint tutorials tomography ADMM. Now I should note here, this case, there is an example in Tau that just solved this, but not with the L1 norm, but with the TV norm here, where D is a dictionary matrix where it's a -1 on diagonal and +1 in the off diagonal to the right side. So this is quote-unquote correct solution, but I'll just go with the L1 norm for easier illustration. And like I said, you could do whatever regularization for to solve the problem, but not all regularizers are made equal. So you could do L2, but it basically doesn't work. Error of 80%. Yeah. And how would you run Tao in PETSc? So like most things in Tao, you just create and you set the type as a TaoADMM, and then you set objective and gradient of the entire thing. So it'll be f plus g in our example. And now we want to say set the A, B, and the C vector, and then routines for the f and g. So previously, this full is for f plus g, and then now you want to set f and g. So I kind of shortened it to fit on the screen. So it'll be actually read TaoADMM set misfit, objective, and gradient routine. And f, you could do either f opt grad or g opt grad, which is a callback function here. Same thing for the Hessian. And then you can pass, and then constraint, it should be constrained Jacobian, but I shortened it. So you could set either A or B, or in many cases, just the identity or negative identity. So you could just pass null, which then just interpret it as an identity. And you can also set the constraint vector and the C. So on Tau, it'll be annoying if you had to implement ADMM on your own because you have to maintain 3 Taus, but ADMM is a nice wrapper that manages all the sub-Tau F and sub-Tau G, and then the parent Tau that overlooks everything. And then, of course, you can solve solver type for F and G. So you could set, so let's say, okay, TaoADMM get misfit subsolver. Misfit is for F, like I said, and you can say, I don't know, Tau Newton line search or whatever that out there. And then, but also if you know you want to have some kind of closed form solution, or you want to provide your own solve, then you could just write your own with something called Tau shell. So F1 regularized, F1 norm plus Lagrangian, there is a known solver, closed form solve called solve threshold. So what you could do is that, okay, you get the type Tau shell, and you in the Tau shell context, which gives you a pointer, and you can set the solve and then this callback function solve threshold, which you have access to the shell context, and then you solve your whatever you want to solve in the solve threshold. Also, in this specific case, we had this lambda for regularizer, which is very common in ADMM format. So we had a special function, so you can set the regularized coefficient, and you can also get it, and then you could, in case you have to update it, you could do it inside of your routines. So this is not a tomography talk, but just to show you that it does work, and then in many cases you should use some regularized that's specific to your need, and then how TaoADMM or gives you options to choose whatever you want to solve instead of using what's there. And then obviously, like many PETSc solvers, there's a lot of options. You could set the coefficient, spectral penalty, parameters, and then there's a lot of new tricks to accelerate the ADMM called relaxation. You could do that. And then also the soft threshold, in this example, I wrote it down, but it's built in where you don't have to do all this. They just do it for you for the L1. So you can just, okay, we want to use soft threshold, so you don't even have to write a shell for this case. And also for the misfit Tau NLS, we just chose NLS, whatever. And then you could set the preconditioner type to whatever you want. So it's very modular, and yeah. So that would be it for the TaoADMM, and I would like to see some inputs from the user side. So that'll be it. Thank you.
Thanks, Hansol. So I personally am pretty excited about these developments that we've been doing. So before Hansol started working on this, there was no shell equivalent in Tau to the kind of supply your own solver that exists in other parts of PETSc. And so this kind of modularity is it opens up ADMM, but it opens up a lot of other distributed optimization and first order based methods, which are different from the Hessian and Newton quasi-Newton based approaches that have been the bread and butter of Tau since its beginning. but are going to be important for applications that we start looking at, the addition of non-smooth terms from statistical measures and from data regularization. Any questions out there? All right, well, if not, Hansol, thanks again for telling us about TaoADMM.